Hello everyone, my name is Sangdup Tamung and my topic for the presentation is Lorenz Transformation, Lane Contraction and Time Dilation. So in Lorenz Transformation we are doing introduction, formula, equation, physical implications. In Lane Contraction we are doing introduction, proper length, example and summary. In Time Dilation we are doing introduction, time dilation caused by relative velocity and derivation and formulation. And in last we are doing the summary of all. So let's move to the topic Lorentz transformation. So Lorentz transformation is the relationship between two different coordinate frames that move at a constant velocity and are relative to each other. The name of the transformation comes from a Dutch physicist Hendrik Lorentz. There are two frames of reference, which are inertial frames, motion with a constant velocity, and non-inertial frames, rotational motion with constant angular velocity, acceleration in curved paths. So I'll just highlight the main points. Lorentz transformation is only related to change in the initial frames, usually in the context of special relativity. This transformation is a type of linear transformation in which mapping occurs between two modules that include vector spaces. Lorentz transformation can also include rotation of space. A rotation that is free of this transformation is called Lorentz boost. The space-time interval which occurs between any two events is preserved by this transformation. So these are the mathematical form of Lorentz transformation, where t, x, y, z and t dash, x dash, y dash and z dash are the coordinates of an event in two frames. V is the velocity confined to x direction. C is the speed of light. Lorentz transformation equation. In the reference frame F, which is stationary, the coordinates defined are x, y, z and t. In another reference frame F, which moves at a velocity v which is relative to f, and the observer defines coordinates in this moving reference frames as x dash, y dash, z dash and t dash. In both the reference frame, the coordinate axes are parallel and they remain mutually perpendicular. The relative motion is along the x dash axis at t equals t dash equals 0. The origins in both reference frames are same. X, y, z equals x dash, y dash, z dash equals 0. In the events x, y, z and t are recorded in reference frames F, then in F dash these coordinates have the following value. So these are the Lorentz transformation, and the above equation are collectively known as Galilean transformation. So the physical implications are: the invariance of the speed of light is one of the critical requirements for Lorentz transformation. This fact is also used in the derivation of this equation. There are three unintuitive but correct predictions of Lorentz transformations, which are lane contraction, time dilation, and relativity of simultaneity. So we are doing the lane contraction and time dilation. So moving on to lane contraction. Introduction. Lane contraction is the phenomenon that a moving object's length is measured to be shorter than its proper length, which is the length as measured in the object's own rest frame. It is also known as Lorentz contraction or Lorentz-Fitzgerald contraction, after Hendrik Lorentz and George Francis Fitzgerald, and is usually only noticeable at a substantial fraction of speed of light. Length contraction is only in the direction in which the body is traveling. For standard objects, this effect is negligible at everyday speeds and can be ignored for all regular purposes, only becoming significant as the object approaches the speed of light relative to the observer. Proper length. One thing all observers agree upon is relative speed. Even though clocks measure different elapsed time for the same process, they still agree that relative speed, which is distance divided by elapsed time, is the same. This implies that distance too depends on the observer's relative motion. If two observers see different times, then they must also see different distances for relative speed to be the same to each of them. Proper length LO is the distance between 2 points measured by an observer who is at rest relative to both of the points. So this is the observer's frame. Length contraction L is the shortening of the measured length of an object moving relative to the observer's frame. L equals L naught root over 1 minus V square by C square. If we measure the length of anything moving relative to our frame, we find its length L to be smaller than the proper length LO that would be measured if the object were stationary. So here I have given the example. Calculating length contraction, the distance between stars contracts when you travel at high velocity. So this has to do with simultaneity and time dilation. So the solution for part 1, identify the knowns, identify the unknown, and choose the appropriate equation, and rearrange the equation to solve for the unknown. The solution for the part 2 is same, identify the known, identify the unknown, choose the appropriate equation, and rearrange the equation. So taking the square root, we find V upon C equals 0.99944. So we have the summary now, that all observers agree upon relative speed. Distance depends on observer's motion. Proper length LO is the distance between 2 points measured by an observer who is at rest relative to both of the points. Earth-bound observers measure proper length when measuring the distance between 2 points that are stationary relative to the Earth. Length contraction L is the shortening of the measured length of an object moving relative to the observer's frame. So these are the formulas. And moving on to the last topic, that is time dilation. In physics and relativity, time dilation is the difference in the elapsed time as measured by two clocks. It is either due to a relative velocity between them or to a difference in gravitational potential between their locations. When unspecified, time dilation usually refers to the effect due to velocity. Predictions of the theory of relativity have been repeatedly confirmed by experiment, and they are of practical concern, for instance in the operation of satellite navigation systems such as GPS and Galileo. Time dilation has also been the subject of science fiction works. Time dilation caused by a relative velocity. Special relativity indicates that for an observer in an inertial frame of reference, a clock that is moving relative to them will be measured to tick slower than a clock that is at rest in their frame of reference. This case is sometimes called special relativistic time dilation. The faster the relative velocity, the greater the time dilation between one another, with time slowing to a stop as one approaches the speed of light. Theoretically, time dilation would make it possible for passengers in a fast-moving vehicle to advance further into the future in a short period of their own time. For sufficiently high speeds, the effect is dramatic. So, this is the graph for the derivation. So, these are the derivation formulas. So, the summary of length contraction, time dilation, and Lorentz transformations. So, length contraction applies when you are talking about a distance that is independent of time. Example, the distance between two objects that are fixed relative to one another, or the distance between two ends of a single object. The proper distance in the formula is the distance in a frame where the two ends of the distance are not moving, and the formula says that the observed distance in another frame is smaller by a factor of gamma. But note that length contraction does not apply if we are talking about the distance between two things that are moving relative to one another, or to the distance between two events. time dilation. Time dilation applies when you are talking about two events that are at the same place in same frame. Example, two ticks on the same clock. In this case, the proper time in the formula is the time in this frame where the two events are at the same place, and the formula says that the observed time between these two events in some other frame is larger by a factor of gamma. But note that the time dilation does not apply if we are talking about the time between two events that are not in the same place in either frame. So Lorentz transformation. When length contraction and time dilation do not apply, or even when they do, we can use Lorentz transformation. Lorentz transformations relate the position and time of a single event in some frame S to the position and time in another frame S dash. If you are applying the LT formula, ask yourself whether the x and t you are plugging is an in correspondent to some specific event. 2. The main steps to using Lorentz transformations to solve a problem. A. Identify one frame of reference and call it S. It is your choice, but usually it is simplest to call S the frame of reference in which you have the most information. Determine the velocity of frame S dash relative to frame S. The velocity v that appears in the Lorentz transformation formula or the velocity transformation formula is always this velocity. Make sure that you have defined the x direction so that this velocity is either in the positive or negative x direction. D. Decide which events are relevant for the problem. Pick some event to be the origin of space and time coordinates. Determine the coordinates and time of the other events in one frame of reference. This might be information you are given or information that you need to work out using ordinary kinematics formula. Example, distance equals speed into time. Finally, you can use the Lorentz transformation formula to determine the positions and times of these events in the other frame of reference. This should be enough information to allow you to solve the problem. So these are the steps. The same steps A, B, and C apply to using the velocity transformation formula or the formula for transforming energy and momentum. Note that the velocity V in this formula is still just the velocity of frame S dash relative to frame S. So I'd like to thank our teachers for the topic and giving us the wonderful opportunity to present the presentation. Thank you, everyone.